Hello and welcome back to Calculus 3, section 13.6 on cylinders and quadratic surfaces. So you're all used to calling a cylinder just a cylinder, right? But it's a broader family of shapes. So to define a cylinder, give me a second, just want to find something. Hold on. So, cylinder refers to a surface that is parallel to a line. So if I take line that goes, let's say, through the center of the circle on the top, every line at the edge of this cylinder is parallel to that line, so we call this a cylinder. So it's like a pipe or your Coke bottle, Coke can, not the bottle, can. But I can take a piece of paper and I can just bend that piece of paper so that the side of that piece of paper is a parabola. That's also a cylinder. It's not round, but think about it. If I define one line here to be a line, every other line is parallel to it. It's a cylinder. So you are used to having a cylinder to be a pipe. But any shape that you can make so that line is parallel, so I'm going to draw a shape where I bent the piece of paper, and let's say I am taking this line as my anchor line to look at. Every of these lines here is parallel to that black line, so this is also a cylinder. So in context of the three-dimensional surfaces, the term cylinder refers to a surface that is parallel to a line. Now, what I have are the lines that are going to define the shape, and we'll call those lines a trace. The blue line that I draw over here, which you can't see the other side, but it's there. The blue line is called the trace. And we're going to have definition of a trace. Definition of the blue line. A trace of a surface is the set of points at which the surface intersects a plane that is parallel to one of the coordinate planes. We have xy trace, yz trace, and xz trace. For every object we have those. It's time to cut this water bottle with the planes and take a look at the trace. When I cut through this water bottle horizontally, this sprayer bottle, whatever, when I cut it horizontally, I'm going to get a circle around, because this is a round object. That circle is going to be called XY trace because I cut this with a plane that is parallel to the XY plane, which is the floor of this room. So we already agreed that our floor is XY because our X-axis was the one with the door, Y-axis is the one with the board, whiteboard here. So if that's X-axis and that's Y-axis, then the floor is XY plane, which means that the floor and ceiling are both XY. The bottom is z equals 0, the top is z equals 10, right, as equations. And any plane that you have in between, like surfaces of your desks and so on, all of those planes are z equals something, but they're xy planes because they're x and y axis as directions, right? So when I cut this bottle with the xy plane, I get the xy trace, and that xy trace would be a circle in this case. So I'm going to draw a cylinder over here and say that, let's go with blue. If I cut with the xy trace is circle. In this case, right? Different shapes will have different stuff. Yes?
So a trace is like synonymous to just a cross section, right?
Yes. Good. Now I am going to take the cylinder and I'm going to cut that cylinder with the XZ plane. And when I cut it with the XZ plane, in this case, XZ plane, let's use orange for XZ plane. XZ trace, in this case, is a rectangle. And then let's use green. And the green will be our YZ trace, which is also rectangle in this case. If you take a ball, each one of those traces, when you cut the ball, is going to be a circle. If you take a watermelon, each one is going to be an ellipse, right? Because when you take a look at the watermelon, you cut either way, you cut the watermelon, you always get an ellipse. Right. So the trace is going to be this equation, the shape that you get, as you said, the intersection, right, of the two shapes, and it's going to give us something in there. So now they have a good example in the book of they're using the elliptical paraboloid. So even if it's a circle, we still call it elliptical paraboloid because we already established that in this class circle is a special case of ellipse, right? When ellipse has the same radius each way, it becomes a circle. So just the same story like square and a rectangle. It's the same shape, it's just square has all sides the same. So it's special. So this guy over here will have the same. So we have a XY trace, then we have this one, and we have that one. So those are all the different traces that we can get. Now, what you guys need to study, I'm just going to say book example, look it up, book example. You know all the letters, right, and stuff, so look it up. This is something. We are turning to the book, page 862. Page 862 in our textbook. And what you see here are 6 of these basic shapes that we want to look at. And we are focusing on the shape, the name, and its equation. The first one is ellipsoid, which is your watermelon. Right, so the first one is ellipsoid. Which is the watermelon. And for this shape, if you cut with any of the planes, you will get an ellipse. Now, those cuts need to reflect in the equation, and equation has to make sense. So equation x squared over a squared plus y squared over b squared plus z squared over c squared equals to 1. If I am cutting with the equation xy plane, which is z equals to 0, right, for the xy trace, if I cut with the xy trace, z equals to 0, and that kills this completely. Oh, you can't see that. If I'm cutting with the xy plane to get the xy trace, I will cut with the z, right? The floor, we said the equation for the floor plane is z equals 0. If I cut with the z equals 0, imagine that this is a watermelon now, and I'm cutting it midway with the z plane, right? Then what we get, oh, it's a watermelon right here, nice. So when I cut the watermelon with the z equals 0 plane, I get an ellipse. Do I get an ellipse? Hell yeah. That's equation of the ellipse in 2D, right? If I cut with any other plane, I always have ellipse left. See that? There's always an ellipse, equation of an ellipse left. So ellipsoid is going to be the watermelon-like shape, and any way you cut, you always get an ellipse, and you see that in the equation because no matter which one of these you scratch off, the remainder is always an ellipse. The next one is elliptic paraboloid, which is the one I drew up there. And when you cut this one, well, let's first write equation is z equals x squared over a squared plus y squared over b squared. So that's our equation. I love this so much. I can't even express how much I love this stuff. Look at this. This is how crazy good math like fits together. If you cut this with any plane above x and y plane, you have to cut with z equals 1, z equals 2, z equals 3. You don't get to cut with z equals 0, because z equals 0 on the bottom will give you 0. And in order for z to be 0, your x and y must be 0, because everything is squared, right? And then you get your 0, 0, 0 point. So you have to cut with a non-zero z. If you cut with a z that is equal to 1, what do you get? You get ellipse, right? Yeah. If you got with z equals to 2, just divide everywhere by 2, it becomes 1. It's ellipse again. So no matter where you cut with the xy plane, you always get an ellipse. Hence, elliptic. Can it be circle? Sure, just get a and b to be the same number. Fine, it's a circle then. But the kick here is that no matter where you cut horizontally for this, this is like inverted umbrella, right? It will be that. Now, if you are to cut x equals 0, which is along y-axis, what do you get? You get z equal y squared. Don't worry about b squared, that's just a number, who cares? What is z equals y squared? Parabola. Do you see a parabola? Of course you see the parabola when you cut, right? So this is the thing that fascinates me for these things, right? So you get all three traces, and they all work out as a 2D equations once you cut and eliminate one of the dimensions. If you cut out y, you still have a parabola. If you cut out x, you have a parabola. If you cut out z, you have ellipse. Elliptic paraboloid. Parabolas and ellipse. Elliptic paraboloid. Cool, right? Next shape, hyperboloid of one sheet. Hyperboloid of one sheet is going to be, that's a terrible hyperboloid. It just goes like that. Hyperboloid of one sheet and that's a y. X squared over a squared plus y squared over b squared minus z squared over c squared equals to 1. Ellipse equation has a plus. Hyperbola, which is inverted ellipse, has a minus. They look the same other than the plus and minus in the formula, if you know your 2D equations. So now, if I am cutting with a z equals 0 floor, I'm cutting out z equals 0, what do I get? I get ellipses, right? We do see an ellipse over here when I cut. Or a circle if a and b are the same. We don't know that. if I'm to cut with either x or a y, I get hyperbola. Hyperbola is this, if you remember your pre-calc. That's the hyperbola. So, and it has a minus. So if I cut x out, you have y squared minus z squared equal 1. That's hyperbola. If you cut out y squared, you still get hyperbola because now you have x squared minus z squared. If you cut out z's, then you're cutting horizontally, and you have your ellipses or circles depending on what you have. Cool, right? Next one, hyperboloid of two sheets. Hyperboloid of two sheets, and that one is going to be like this. Which is x squared over a squared plus, it's a terrible a, plus y squared over b squared is equal to z squared over c squared. So for certain values of z, you have ellipses. And if you cut z high enough or low enough, you are going, that depends on the numbers you have of a, b, c, and so on. So if you cut high enough, you cut low enough, you are going to get ellipses, because this becomes a number. It can't be a 0 because there is nothing at 0, and that requires x and y to be 0 and so on. So if you cut with the z equals 1, z equals 2, z equals 10, whatever works, whatever numbers you get, you will get ellipses and circles as trace. Now, if you cut with y or x, they become numbers. They go to the right. Z moves to the left, becomes negative, and you get your hyperbola. Now, these hyperbolas are going to be like this. Previous one sheet, was a hyperbola that looked like that. So this was for one sheet, and this is for two sheet. So horizontal and vertical hyperbolas are giving us these two. The next one is elliptic cone. Elliptic cone. Uh-oh. That's the elliptic cone equation. That's the elliptical equation, because when you cut with the z equals hold on, if z equals to 0, then x and y must be 0. You are getting the 0, 0, 0. Good. When you cut with x equals 0, then you have y equals plus minus z, which is linear. Holy nightmare. Okay, sorry. So you gotta fix this, guys. Hyperbolic of the hell did I do here? Ah, okay, got it. So let's talk about cone, then we'll come back to the hyperboloid of two sheets. So for cone, if you are cutting with z equals a number, if you cut with z equals a number, you get your ellipses. So any cut that it's horizontal will create traces which are ellipses or circles depending on your a and b. If z is 0, then x and y must be 0 because they're both squared and they're always positive, so there's no way to subtract them into 0. So the only way to get this point is if z is 0, then x and y must be 0, and that's what you get for the point. So for z, you either get circle slash ellipse or you get a 0, 0, 0 point at the origin. If you cut out x, then your equation is y squared over b squared equals z squared over c squared. You don't have to worry about, these are numbers, so you don't have to worry about them at all. You can just worry about variables. And if you square root both sides, you get that y is equal to plus minus z, or if you want to say z is equal to plus minus y, no one cares. These are 45-degree lines, like that, which is exactly what we see as a trace. So whether you cut in x or a y, you will always get these intersecting lines. Now they're going to be at an angle. This is 45 because the slope is 1, but these guys will give you the slope at which they intersect. So that's that. Great. Back to hyperboloid of two sheets. The equation for this puppy is you switch all of the signs here and you leave one alone. So negative x squared over a squared minus y squared over b squared plus z squared over c squared equals to 1. Much better. Now, if I cut with z equals 0 and I just cut this out, well, we get the equation, and you move the minus to the other side, you don't get the equation of the ellipse because it would be x squared plus y squared equals negative 1, and that's not the equation. So z has to have a non-zero value, and depending on a and b, it will cut into the object eventually. So providing z equals 1, 2, 3, or 10, whatever you need, you will eventually start cutting these, and then you will have ellipses, because this z would become large enough to become bigger than 1, that whole term, and when you subtract 1 minus z squared over c squared, you will get a negative number. And then you multiply through by negative, it eliminates all negatives, and you finally start getting ellipses. In terms of the other ones, it's clear. If you eliminate x, you have z squared minus y squared, that's hyperbola. If you eliminate y, you have z squared minus x squared, that's also hyperbola. So those are easy. The only one that is tricky is z, because not every value of z provides you with a trace. Z squared over c squared must be bigger than 1 in order for it to produce a negative number on the right hand side when combined with this one, so that you can multiply everywhere by a negative to come up with the ellipse. Hyperbola, sorry. No, ellipse, I said it right, ellipse. So those are the first 5, and now the grand finale. Hyperbolic paraboloid. also known as saddle. Have you ever seen horse saddle? It's a hyperbolic paraboloid. That's what it is. All right, so to draw this shape, it's hard.
It's like a wave.
It's a saddle. Here, look, saddle. You can't argue that.
So
It's a saddle. It's look. You know the letters. Z equals x squared minus over a squared minus y squared over b squared. That's the equation. I can even do this. Now, I know that you are dying to actually see this shape, so here. I'll make it larger. See that?
Oh my god.
Whoa. I'm serious.
Is that a wolf?
It's a horse.
It's a dragon.
Not a horse.
Did the horse have fangs?
But give him a name.
There you go.
Unicorn?
It's a saddle. Clearly it's a saddle. By far, this is the coolest object. Don't worry about the rest. This is the coolest object that we have. You have never had anything remotely similar to this. There is a really, really cool feature here. This point at the origin. This point at the origin. What is that point?
Saddle point.
Okay, it's a point on a saddle, fine. What's so cool about that point?
Parabola. Hyperboloid. All of them. It's a parabola. What's that?
It's a parabola, yeah, sure.
Well, it's.
You have never seen a point like this before. This point doesn't exist in your 2D mathematics that you have seen so far.
Is it because it's right in the center of the parabola that goes, that's the, like, the Z?
That's half of the story. I need the other half to it, and then we can finally start breaking our heads on what that point actually is. Again, you do not have anything like this in a 2D math, because it's impossible to have it in 2D math. But in 3D math, there it is. You calling it a saddle point? I love it. We're going to keep calling it saddle point for the rest of the course.
Doesn't it have like no slope? Like no defined slope?
Excellent. Why?
Because it doesn't.
Is it because it's the meeting point of each parabola? Like if you take the cross section of each side, it's.
Okay, so what? 100% of what you said is correct. So what?
You can't define one slope from that because it's.
I can go with a different direction. I can have a separate slope in x direction and separate in y, which will actually be partial derivatives coming up soon. Can you tell me anything about, so to think of, I want you to think along the lines you suggested of those traces, of the cuts. You told me about two parabolas. What is this point to those two parabolas?
Oh, well, it's one's apex.
So
There's no
can you
trace.
use a different word other than apex?
It's one's absolute maximum, one's absolute minimum.
That's it. Do you see how crazy this is? This point is a minimum and maximum at the same time, depending which way you look, right? If you look from the front where the horse goes, it's a max. But if you look sideways where the person goes, it's a min. You don't have that in 2D math, right? Welcome to 3D realm. And we call those types of points saddle points. So when we later, right, next chapter, when we do min-max calculations, optimization, we are going to look for minimum, maximum, and saddle points. We'll have a completely new creature because of that. Yes?
So can you not have a trace there? Because
There is a trace. Trace is just fine. It's a parabola, right?
Okay.
Trace is a parabola. You kill your y, and I mean I'm going back now to
The wolf is in the way.
the wolf. I called it. I didn't put the wings. That's the problem.
Yeah.
Oh, unicorn. My bad.
Right. Unicorn with
Dragon.
wings.
Dragon.
It's a dragon. I've been drawing this thing for 10 years. I perfected it, and you still call it a wolf? If I had feelings, they would be so hurt right now, you have no idea. All right, so guys, we're going to kill the y direction, and you have z equal x squared. That's a parabola that opens up, has a minimum. Now I'm going to kill the x direction, and you have z equal negative y squared. That's a parabola that opens downwards, has a max. Right? And if z is equal to a value, you get hyperbola, therefore hyperbolic paraboloid. Right? If z is equal to, let's say, 1, you get your hyperbola. So you have two parabolas, one opening up, one opening down. And then you have a hyperbola when z is equal to a value. Therefore, you get your hyperbolic paraboloid, which is really cool. The last thing, what do we have, 8 minutes, that I want to mention is that once we move to the third-dimensional realm, if we need to do the geometry on our class ends at 10:15. Yep, that's the. Yep, thanks.
All right, have a good one.
Me too.
And if I don't see you tomorrow, well, actually, you won't see you.
See you Tuesday.
You all have a nice Memorial Day weekend.
Yeah, it's you too. Right, thank you. You too. So the our geometry on the curved surfaces is not the same as the geometry on a flat plane. What is the sum of the angles in a triangle on the flat surface? 180. Great. So if I draw isosceles triangle like this, so going 4 units, and then I go like this. Each one of these angles is 45, 45, and then a 90. They add to 180 total. Right? Great. Now I have planet Earth, and I have the North Pole, and then I am going to start at the North Pole and walk straight down to the equator, which is the middle line. I'm going to turn 90 degrees and walk quarter of the length of the equator, and then turn right and go back up, and that's 90 degrees as well. So now I already have 90 plus 90 which is 180 in this triangle. Now, if you look at the top, remember what I did. When you look from the top, I walked down this way, and then I went quarter of the Earth's equator, and then I went back to the North Pole. So you see that there is 90 degrees up there as well. So what's the sum of the angles in this triangle? Is 270. So your geometry that you learned, which is called Euclidean geometry, which is the only geometry you know so far, does not apply anymore on curved surfaces. If you take a cereal bowl and you draw a triangle inside, the angles will add to less than 180 degrees. Parallel lines on a curved surface intersect. Oh, you never heard of those? Can you please tell me what these are? This is north, this is south. Ah. Yeah, they're parallel. They intersect at the south and north pole. Beautiful, huh? And the shortest distance is no longer a straight line. If you go to, this is something that not many know. This is the last thing we're going to look at. You ever been on this website? Flight Radar 24? You should. It's really cool. What this website does is traces all air traffic live. Here's the United States. Wow.
That's insane.
That's just commercial, right? The air with passengers. And let's pick one of the flights that it's going across the ocean. There are some of them going, as you can see. Do you see that they're all following the curved path? Right? Between US and Europe. They're all going in a curve. Because if they ran straight across, they're going to run out of the fuel because the Earth is fat. So it's longer. The way to find the shortest distance on the surface of the planet is you need two locations, let's say New York and London, and then you need the center of the Earth, and then you create a plane, and then that plane between these 3 points will intersect the surface of the Earth, which would give you the curve called geodesic, and that curve is the shortest distance between the 2 points. Anything else is going to be longer because you have to go over the hump, right? Because the Earth is a ball, it's a curve, so the shortest distance is actually going to be not the straight line between the two, but the curve slightly above, and you can actually see it there. So you have enough fuel to actually fly over, so you can, right? Because you don't, I mean, no one says, just tank it up, whatever, and then we'll just stop along the way if we need more gas, right? You're going to a birthday party. There are no gas stations along the Atlantic Ocean for you to stop and refuel. And also you don't want to just bring a whole bunch of extra fuel because you don't know how much you need, because passengers have bags that you can charge, $700 per bag to make profits. So, right? Cool. That's our chapter 13. Next week, chapter 14, and we'll talk about the exam on Thursday. Ciao.